Welcome back to The Deep Dive. Today we're diving into something, well, visually stunning. It takes the invisible pressure of sound and somehow forces it into these breathtaking geometric shapes.
Yeah, it's pretty incredible stuff.
You know, you think about science history, Michael Faraday, he made electricity visible, right, with magnets, iron filings, but sound waves, how do you actually see the sound in this room?
That's exactly the question Hans Jenny really dedicated his life to. He wasn't just mapping fields like Faraday. He was trying to map vibration itself, make it visible.
So Hans Jenny, he was a Swiss physician and educator, and he coined this term, cymatics. What's the basic idea?
Cymatics, yeah. It's basically the study of how waves shape matter. Jenny, working mostly mid-20th century, used pretty straightforward tools, actually.
Like what?
Things like a loudspeaker, a tone generator for precise frequencies, and then simple stuff like fine powders, liquids in a dish.
And he'd vibrate them.
Exactly. He took those invisible sound oscillations and turned them into these incredibly crisp geometric forms. Suddenly, a simple tone becomes visible as a star shape or a hexagon or these intricate labyrinths.
It sounds almost magical, but our mission today, for you listening, is maybe to look just beyond those beautiful pictures you see online.
Right, because the images are dazzling, almost hypnotic.
Yeah, and we want to get into the core of Jenny's method and maybe how modern physics, what we call motion theory, takes that initial sense of awe and turns it into something, well, practical, a design tool.
Yeah, it's the key transition, isn't it? From wonder to prediction.
Definitely. So before we jump into the modern engineering side, what was Jenny's big idea? What did he think these patterns were actually showing us?
Well, he had this really elegant kind of three-part thesis driving his work. First, he argued that oscillation reveals order, meaning if you drive matter with a periodic force, like a steady sound wave, even if it starts out looking chaotic, it organizes itself. It finds these stunningly repeatable forms, and those forms are dictated by the driving frequency.
So the order is always there, just hidden, until you shake it the right way.
That's a great way to put it, yeah. And his second point was crucial. Boundaries matter.
The container.
Exactly. The plates, the membranes, the dishes, they weren't just passive holders. They act like filters. They select which vibration patterns or modes are allowed to exist. So the patterns don't just smoothly morph, they jump subtly, abruptly, into a new complex shape the moment the frequency crosses a specific resonance point that the container allows.
It sounds like the vessel itself is sort of speaking the language of the vibration, or choosing it.
It absolutely is. It's constraining the possibilities. And his final point, which was really important for him as an educator, was that seeing is insight.
Makes sense.
Jenny really believed that by showing these processes visually, he could spark intuition. Help people see connections maybe between acoustics and biology or physics and art without having to wade through heavy math equations right at the start. It was an invitation, really.
An invitation to see the hidden structure. Okay,
Right.
let's unpack the visual magic itself. The classic demo everyone knows, or has maybe seen, is the Chladni plate.
Ah, yes, Chladni. Ernst Chladni was actually doing this way before Jenny, but Jenny really popularized it and explored it systematically.
Right. So you sprinkle powder, sand usually, on a metal plate hooked up to a vibration source, turn on the sound, and boom, the sand flies into these perfect symmetrical shapes. How does that actually work? What's the physics?
Okay, so here we shift from the magic to the physics, which is just as elegant, I think. The plate itself, when driven at a certain frequency, can only vibrate in specific ways, these standing patterns called eigenmodes.
Right.
Now, what happens to the powder? It's basically about acceleration and friction. The sand gets kicked around violently where the plate is moving the most. Those are the antinodes, the spots with high acceleration.
So it flees the chaos.
Precisely. It migrates away from those high energy zones and settles where the plate is relatively still, the quiet spots.
Which are the nodes. So the pattern we see is literally a map of the plate's quiet zones. Like the sound wave draws lines saying, settle here.
That's a perfect way to visualize it. The system finds a low-energy resting place for the powder. The grains are constantly being pushed out of the hyperactive zones, and they can only come to rest where that vibrational energy is minimal.
So the pattern isn't just the wave, it's the wave plus the material.
Exactly. It's the inherent mode map of the plate, but it's filtered through the friction law of the powder. Change the powder, you might subtly change the pattern details. The material really matters.
And it's not just powders. Jenny did amazing work with liquids, too. We see Faraday waves.
Michael Faraday noticed these back in the 1830s.
So you vibrate a container of liquid vertically, and the surface itself erupts into these incredibly ordered standing waves, sometimes square grids, sometimes these rotating hexagonal cells. It's almost unnerving how organized it looks.
Yeah, in liquids, things like the container shape, its depth, the fluid's viscosity, and of course the frequency, they all define this kind of discrete menu of possible surface
And
patterns.
a menu of shapes.
And a critical detail with liquids is that the vibration also drives internal flows, tiny currents called streaming flows.
Okay.
These flows act like little conveyor belts. They transport any tracer particles, like dye or tiny bits, within the fluid and deposit them along those persistent nodal lines, essentially highlighting the underlying wave structure,
Yeah.
which makes it even clearer.
What gets me is the universality. You see these basic mode shapes repeating across completely different materials, a metal plate, a tub of water, even like thick honey or gel. They all seem to obey the same underlying rules, this grammar of nodes and antinodes. It seems universal.
It really is. And that brings us to sort of the core motion theory definition of what a pattern is. A pattern, fundamentally, is a stable loop. It's a standing wave that's robust enough to survive the energy loss, the leak. That's always happening in any real system.
Leak, you mean like friction, viscosity.
Exactly.
Yeah.
Friction, viscosity, air resistance, sound radiation. Energy is always leaking out. The material you choose, the powder, the plate, the liquid, determines the specific leak law. And that leak law acts like a harsh editor. It selects which potential patterns are strong enough to persist and which just fade away instantly.
So the constraints, the material, the container, the frequency, they're the real sculptures here, not just the sound itself.
You've absolutely nailed it. If there's one core idea to take away from this part, it's this. Sound doesn't draw geometry. Sound plus a vessel selects it. The vessel, the boundary, the material, that's the critical partner. It's non-negotiable.
That concept, pattern selection by boundary and drive, it's aged incredibly well, hasn't it? And it feels very modern.
Totally. And that's why Cymatics isn't just some, quirky historical demo. It serves as a really friendly gateway concept.
How so?
It makes complex ideas like resonance, modes, standing waves, things engineers deal with constantly. It makes them visual and intuitive.
Right. You can literally see the nodes, the quiet spots, and the antinodes, the high-energy hot spots. And it helps understand that other crucial idea, the quality factor, or Q.
Q factor. Yeah, that one can be a bit abstract.
Can you give us a simple analogy? What does Q factor mean in this context? How does it relate to the patterns?
Sure. Think of Q as a measure of how well a system stores vibrational energy, or how pure its resonance is. A high-quality bell, when you strike it, rings for a long time with a clear tone. That's high Q.
Okay.
If you hit, say, a wet cardboard box, it just goes thud. The sound dies immediately. That's very low Q. In Cymatics, a system with high Q means the patterns that form are incredibly sharp, distinct, and stable. They lock in cleanly.
Even if the frequency isn't perfectly steady?
Yeah, a high Q system is more forgiving of slight variations. It wants to resonate at its preferred frequencies. A low Q system is mushier. The patterns might be fuzzier, less defined, harder to excite. It leaks energy too quickly.
Got it. And this ability to structure energy, to create these zones of high and low activity.
Yeah.
This isn't just for cool demos anymore. It's driving real technology.
Oh, absolutely. Far from just lab history. The exact same physics, using sound waves to create these invisible fences and quiet zones, is the engine behind several pretty major fields now.
Like what? Give us some examples.
Okay, we'll take acoustophoresis. Scientists use carefully shaped sound fields, standing waves, inside tiny fluidic channels. The low-pressure nodes in these waves gently trap and move microscopic things, like cells.
Sorting blood cells, maybe?
Precisely. Sorting blood cells, isolating rare circulating tumor cells, handling delicate biological samples, all without physically touching or potentially damaging them.
They're using the quiet geometry inside the wave for ultra-gentle handling. That's clever.
It is. And the same basic idea, nodes and antinodes, is behind acoustic levitation.
Making things float.
Yeah, using intense sound waves to create stable pressure pockets in midair. You can hold small objects, droplets of reactive chemicals, tiny components, even molten metal blobs suspended, with no contact. Great for containerless processing.
Wow.
And then there are surface acoustic wave chips, SAW chips. These are tiny devices, usually on silicon, that use very high-frequency vibrations traveling along the surface to manipulate fluids on a microscale, mixing tiny amounts, pumping droplets. It's all controlled vibration.
So the cymatics vibe might feel a bit retro, but the fundamental physics is powering some serious 21st century microengineering.
Definitely.
Okay, now we have to touch on the caution you mentioned earlier. Jenny was an early pioneer, right? And pioneers sometimes, well, they get excited and maybe extrapolate a bit too far.
Yes, and it's important we maintain scientific rigor here. The visual appeal of cymatics is undeniable. Some patterns, especially in liquids, look incredibly similar to biological forms.
Yeah, you see pictures that look like cell division or membranes forming or jellyfish.
Exactly, and that resemblance is striking. But
Yeah.
we have to be really careful about jumping to conclusions, about making causal claims that sound alone creates biological form.
So admire the pattern, but don't assume a jellyfish is shaped by ocean acoustics.
Pretty much. Look, the cymatic patterns are beautiful demonstrations of physics.
Yeah.
They are fundamentally just maps of specific boundary conditions and drive parameters acting on a particular material.
Okay.
Living things. Their morphology, their shape, is constrained by a whole lot more. Genetics, complex biochemical pathways, intricate growth feedback loops, evolutionary history, mechanisms that a simple vibrating dish of water just doesn't have.
Right. Different rules apply.
The visual analogy can be inspiring, it can spark questions, but the scientific rule has to be. Let's avoid those sacred geometry claims or implications that sound holds some mystical key to life's forms. These patterns are physics, plain and simple, not cosmic blueprints.
That distinction is critical. Moving from just appreciating the beauty, the awe, to actually analyzing and predicting it, which is the perfect lead-in to our final section.
Right.
If we want to go beyond just watching the sand dance, if we want to actually predict which shape will show up at which frequency in a given setup, we need to get quantitative. How does modern motion theory sort of harden Jenny's qualitative work into predictive engineering?
Yeah, this is where we move from demonstration to design. We basically transform the setup into a kind of dashboard. Imagine you're an engineer tasked with designing, say, a new acoustophoresis chip for sorting delicate stem cells reliably.
Okay. Need it to work every time.
Exactly. You can't just rely on pretty pictures. You need quantitative operational metrics. Motion theory gives us 4 key ones to define the system's behavior.
Okay, what's the first metric on this dashboard?
Metric 1 is the spectrum modes. You absolutely have to measure the system's resonances precisely. Where are the peaks? How sharp are they? This gives you the allowed frequencies and those key factors we talked about. It's the complete inventory of all the possible patterns the vessel could theoretically support.
So that's the menu of available shapes. Got it. What's next? We need stability, right?
Yep, that's metric 2, the leak budget.
Yeah.
You have to quantify all the ways the system loses energy. Viscous drag in the fluid, friction between particles, sound radiating away, heat, everything.
Why is that so important?
Because this budget determines how much sound energy you need to pump in just to sustain the pattern against those losses. It also tells you how quickly the pattern will disappear when you turn the sound off. It's why a water pattern vanishes instantly, but maybe a pattern in thick syrup persists for a bit.
Okay, menu and stability. Metric 3.
Metric 3 is the coupling map, C. This quantifies how effectively energy moves between the different parts of the system. How strongly does the vibrating source, like a piezo ceramic, actually couple its motion into the fluid? How much of that fluid motion then couples to the particles you're trying to move?
Ah, like efficiency of energy transfer?
Exactly.
Yeah.
If the coupling is weak, you might need huge sound power just to get a tiny effect on the particles. If it's too strong, maybe things get chaotic instead of orderly.
Yeah.
You need that Goldilocks coupling.
Right, mapping the energy flow. Okay, that's 3. What's the final piece?
Metric 4 is the transport law. This gets down to the nitty-gritty physics at the particle level. How exactly do particles move during one single sound wave cycle? And how do they drift or stream over many cycles? You need to calculate the forces acting on them.
So not just knowing where the nodes are, but the detailed path the particles take to get there.
Precisely. What forces push them? What forces resist them? Is it pressure gradients? Is it acoustic streaming? Is it radiation force? You need that mechanism defined.
Wow, okay, that's a level of detail far beyond just observing. The difference is huge. Jenny runs a demo, points, and says, look at that cool hexagon. With these 4 metrics, you can say, okay, if I set my frequency to exactly 25.4 kilohertz and the amplitude to X, I predict a stable hexagonal pattern will form in 1.7 seconds, concentrate 95% of the particles at the nodes, and remain stable for 12 seconds after power off.
That's the goal. That's the power of prediction moving into engineering design. And Modern researchers are using this framework right now. They're running falsifiable tests, kind of embodying Jenny's spirit of exploration, but with this predictive rigor.
Like building mode atlases. What does that mean?
It means systematically mapping out the expected patterns, creating a library almost.
Yeah.
Researchers might aim to predict, say, the first 3 dominant patterns you'll get for a circular container versus a square one, or shallow water versus deep water, or water versus a viscoelastic gel, before they even switch on the oscillator.
And then they test it.
And then they test it. Does the experiment match the prediction based on the measured metrics? If yes, great. If not, why not? Which metric needs refining? It's the scientific method applied to pattern formation.
And you mentioned something called acoustic morphogenesis sober version. What's that about? Testing the life analogy.
Yeah, that's kind of the cutting edge, testing the limits of that biological analogy in a very controlled way. Can we use standing sound waves to guide the assembly of inert, non-living soft matter? Things like lipid vesicles, which are like primitive cell membranes, or complex colloidal suspensions.
Can sound make them form specific shapes?
Can we force these non-living blobs to arrange themselves with the symmetry dictated by the acoustic notes? If yes, it tells us where and how simple physical forces can influence soft matter organization, giving us clues relevant to biology. If the assemblies ignore the sound field or form different symmetries, it tells us we absolutely need to invoke other mechanisms, chemistry, specific binding, etc., for biological complexity. It defines the boundary of the analogy.
So in the end, this whole journey, powered by motion theory, really extends Jenny's original observations. It takes it from analogy to actual design.
Absolutely. We're seeing engineers using these predictive mode maps for really cool applications. Growing crystals with specific, highly controlled symmetries by placing seeds at nodes, optimally placing tiny sensors within complex vibrating structures by knowing where the quiet spots are. And as we mentioned, literally manufacturing materials by steering where particles deposit using carefully shaped sound fields, essentially, printing with sound.
That is quite an evolution from shaking sand on a plate. It feels like Hans Jenny's true legacy isn't some secret code hidden in the patterns.
No, not at all.
But rather a powerful method, a way of probing systems. Drive it, vary the parameters like frequency and amplitude, and carefully observe which patterns manage to survive the inherent constraints.
Exactly. And that method provides this fundamental bridge. It connects simple classroom physics demos to high-tech labs working on microfluidics, material science, and even things like noise control, making quiet rooms by understanding modal structures. Jenny's photos were always, I think, an invitation.
An invitation to see.
To treat reality itself as structured motion chosen by constraints. Everything that exists stably exists because it found a way to persist within the rules of its environment.
Okay, let's leave our listeners with a final thought to chew on, something provocative. Why do these Cymatics demos, these non-living patterns, feel so strangely familiar, almost biological?
It's a good question to ponder.
They feel alive, I think, because they clearly show selection. Out of countless possible ways for the sand or water to move, one specific ordered shape wins. It gets selected and becomes stable.
That's a key aspect, selection under constraints.
Yeah.
But maybe ask yourself, what does life add that a passive pile of sand or a dish of water fundamentally lacks?
Growth. Adaptation.
Growth laws, yes. And memory. A grain of sand on that Chladni plate instantly forgets the pattern it was part of 5 minutes ago if you change the frequency. Its state depends only on the current driving conditions.
But a biological system.
A biological system carries its history forward. Its structure today is built upon the constraints and forms of yesterday, influencing how it responds tomorrow. So when you see any stable pattern, not just Cymatics, ask, yes, what physics formed it, but also what specific constraints selected this pattern over others. And crucially, what happens when that pattern gains the ability to grow, adapt, and remember its past?
That's where physics meets biology, perhaps.
That's maybe where the deeper mystery begins.